The next speaker is Henry Tseng, and the title is Tamashii, Create Rails IoT Application More Easily.
Hello, hello, hello. Okay, can you hear me? Okay, good morning, everyone, and hope you have a wonderful party and RubyKaigi last night. And it's very appreciated for you to attending my speaking. Okay, today is my honor to introduce Tamashii to you. The purpose of Tamashii is to make it easier to create Rails IoT application, and I will share some idea for creating Tamashii and the application that's based on it. This is a talk of today's outline of today's talk, and we will first give a short introduction about Tamashii, and then we will take a look at some project that is built with Tamashii. Then we will have demo videos for them. After that, we will show more detail about Tamashii on client side and server side. And finally, we will go to the conclusion. Before we start, I want to introduce myself. I'm Henry Tseng, a Ruby and Rails developer from Taipei, Taiwan. I love Ruby, and I use Ruby to develop web, combined tools, and even games. I work for 5 times Ruby. 5 times Ruby formed by a group of Ruby lovers in Taiwan. We work toward to help the Ruby community in Taiwan growing up. We work hard and play hard, and our people are very nice, and including our 2 adorable cats over there. And here, a lot of cute cats. Woo. Okay. Okay, 好. Let's talk about sorry. Okay, let's talk about Tamashii. Okay, Tamashii is a Japanese word, and it stands for the soul or the spirit. Why we call it Tamashii is that we hope we can get the soul to a device, so we can control the device more easily. In short, we can say that Tamashii is the Ruby-based framework for easy integration between IoT devices and the Rails. It covers both client-side and server-side. Currently, we implement the Tamashii on a Raspberry Pi, and Tamashii provides a way for you to control the devices with the elegant Ruby code. For the server side, the Tamashii server is rack-based, so it is more easy to integrate the Tamashii into the existing Rails application. For details, Tamashii has following features. It has better hardware component management. The data exchange will follow an event-based manner. The networking model is based on WebSocket, and it provides an easy way for you to integrate the Tamashii into the Rails. For hardware component management, we implement and test the Tamashii on Raspberry Pi. So the hardware here means those extra components that can be installed on the Raspberry Pi, such as RFID readers, motors, LCD display, keyboards, and buzzers. Tamashii wraps this hardware with high-level API layer. So with Tamashii, users can write high-level logic to drive the devices without knowing the tedious device protocol. Although this may hide some advanced features from user, but for Tamashii, we think provide easy interface is much more important. This is like the Rails does. Here are some example code to show that the API of Tamashii. You can see that we can make all hardware components into Ruby objects. You can interact with them with elegant Ruby code. The first example here is the buzzer. Buzzer is the small speaker that can play beep sounds. The code here is very simple. You just need to call the method beep and give the number of sounds you want to play as a parameter. The second example is the LCD display. It can print some simple text on its screen. You can see that we just print the messages like you print the message on your Rails console. The next example is the RFID reader. The RFID card is similar to the Suica or Eco card in Japanese metro. It can read the data from your card and send it to the server. Although we can operate the device mentioned above with high-level API, we usually don't use them individually. Instead, we will combine them together. Tamashii employs an event-based manner for data exchange between multiple components. Here, imagine you want to play a song and show some messages when you read the data from RFID reader. The following figure will describe the event-based manner. First, when the RFID card is detected, the card reader will emit an event and send it to the Tamashii manager. Then the Tamashii manager will dispatch those events to components like speaker or LCD display, and you will perform some actions, for example, play song or display some messaging. Let's talk about networking. It is one of the most important things when we build an IoT application. When a client device reads the data from RFID reader, it needs to send the data back to the server and receive following instruction. For example, we want to read an user ID from the RFID card and check with the server database. Then we will show some messages on the LCD display. Also, the server may need to send some messages to client without any request from client. For example, server can push new updates or request the client to restart the devices. If the two-way communication is the only thing we need, maybe a simple TCP connection is sufficient. However, we want to integrate the device into Rails more easily. So we decide to use the WebSocket to implement the networking of the Tamashii. WebSocket is part of the HTML5. It allows us to establish a two-way communication between the server and the client. With it, the server push notification can be implemented with less overhead than traditional polling. WebSocket uses the same port as HTTP, so we don't need to worry about the proxy settings and the firewalling. WebSocket also supports transport layer security, just like HTTPS. And the WebSocket is not new already. Many modern web servers and frameworks support WebSocket, such as Rails and Puma. Because we are using WebSocket, so it's much more easier to integrate the Tamashii into Rails. We create a rack-based Tamashii server. The server uses WebSocket to communicate with the client and use the Redis to store the information about client. We also have the device management protocol. We define some events that is shared by the client and the server. The events can be classified as two major categories. They are data events and command events. Data events are for the sensor data sent from the client. For example, the card data read from the RFID reader. The command events are the server to client commands. For example, we can request the client to reboot the device or play a song. Tamashii server also provides a model-like API for devices. It hides all low-level operation and only exposes the abstract device operation to users, just like the Rails model hides the database connection from users. Here, imagine you want to find a device with the serial number 1234 and make it play 3 songs. Oh, you only need to use the find by method with the serial number with the parameter, and Tamashii will find the device for you. Then you can call the method beep with parameter 3. The Tamashii will handle the rest of things, including querying devices, encoding, transfer, decoding, and process the command. The web developer don't need to know the detailed operation about the devices, just need to treat the Tamashii device as the Rails model. Here we have the first demo video here. This video is about the device management. In this video, we will send the unsynchronized command from server to client. We will first create a song at client, and then we will restart the client devices. We have the web console. And we restart the client. We can see that the last report time is disappeared here, and we will wait the devices to come live. Okay, the device is reconnected. This demo shows that we can control devices directly with the Rails application. Okay, before we go into the details about Tamashii, I would like to introduce two projects that's already built on Tamashii. The first project is the check-in system for conference. The main purpose of this system is to track the flow of attendees. We will explain the detail later. And we have deployed this system on the Rubyconf Taiwan last year. The logo is over there. And we have 17 devices and 270 attendees. And the system works fine. Another project is the access control system. The system allows the remote administrator to decide whether to let a user pass the gate or not, like the Tokyo Metro or subway. We will also explain the detail later. Different from the checking system, the access control system is still under development, so we haven't deployed it for production yet. We will first look at the checking system. As mentioned above, the system of checking system, the purpose of checking system is to check the flow of attendee. With this data, we can know which session they attend or which sponsor they visited. The check-in system has two stages. They are registration stage and the check-in stage. In the registration stage, we will give every attendee a RFID sticker, like the picture here. It's a very small sticker. And we will attach this sticker to their badge. This sticker is like an electronic ticket, like a Suica or EcoCard, but it's very small. And when the user is checking, we will bind the attendee with their RFID sticker to the server here. And we can have their data on the server's database. Then, in the check-in stage, we will deploy many check-in devices at the entrance of each conference hall and the sponsor's booth. After registration, the attendee will bring their RFID sticker with them and attend a section or visit sponsors. They will check in with the RFID identifier with those devices. The devices will send the RFID sticker card data along with the device information. So the server can find out who attend which session or visit which sponsors, and we will record their behavior here. We also have a demo video for the checking system. We have two devices, register and check-in. We first register the user to the database. Then we will check in the user. We can know that who attend which section and which sponsor. Here we have two cards. This is registered card and this is new card. It means the card is registered and you are successfully checking. Okay, now we will register this new card to the website. The ID is updated here. So we will know that this card is corresponding to specific user. And we can take a look at the check-in records on the web console. The counter will increase. So we can know that how many times they visited the sponsor or the session. Okay, now let's take a look at a access control system. This system is, the purpose of this system is to remotely control the gate for entrance. This system is similar to a check-in system. It also needs to registration. But the difference is that we can control the devices on the web console. The devices can allow the user to pass the gate or deny the user and show some error messages on the screen. The following figure will describe the workflow when the user checks in. Different from previous checking system, there is a admin panel on the server side. When the user checks in, the device will send the access request to the server, and then the administrator can decide whether to let the user pass the gate or not. The check-in device will respond to the administrator decision. For example, it can show the error message when the user is denied it. This is a short demo video for the access control system. Here, the user requests access. You can deny the user or allow the user to pass the gate. Here we will deny the user first. It plays 3 sounds. The counter will increase when the access is granted. Although we just play the sound here, but if you have some gate device or door, you can make it open the door or close the door. Okay, we have gone through the high-level introduction about Tamashii and 2 projects that are based on Tamashii. In the later part of my talk, where I will talk about the technical details about Tamashii. Let's look at the client side first. I will talk about the device wrapper for single component. The device wrapper will hide the detailed device protocol from users. It only exposes the high-level API, so we allow the user to operate the devices without knowing the low-level detail. Then, we will have many components to manage, so we need a robust and elegant model. As mentioned before, our concurrent model is multi-threaded and event-based. I will talk about how they cooperate with each other. Finally, we will connect the devices with internet. To handle both synchronized data and asynchronous commands, we use a future-based asynchronous networking model. This allows the client to issue multiple requests to the server. At the same time, it can keep great reactivity to the server commands. The device wrapper will hide all low-level hardware operations from users. For example here, we want to drive the I2C LCD display to show a single letter, the capital A. Even with the powerful I2C Ruby gem to hide the I2C related hardware operation, we still need to write 6 bytes of data to display that single letter over there. A lot of byte command and just display a single text. So how many bytes we need to display welcome to RubyKaigi until 17? I don't know. Okay, so we wrap this tedious stuff in a Ruby object. We hope to let users focus on the behavior. So with device wrapper, users don't need to rewrite their code for different hardware model. Like this. We have a Ruby object called LCM1600-2I2C. It has the method called print, and we will print the message with those tedious protocol, and user don't need to know that. Although this means we need to handle the issue of different hardware components in the Tamashii, we still think it is necessary. Just like the Rails model, FT-Raker will hide the different implementation from user database, for example, Postgres and MySQL. Another example for device wrapper is the RFID reader for metro system in Japan or Taiwan. We know in Taiwan we have Easy Card or iPass for Taipei Metro. It's based on the Mi-Fare system. Meanwhile, the Felica system is used in Japan's Suica or Ikoka. This is developed by Sony. And we know that different countries use different card readers. For example, we may need to use this NFC522 to read the Mi-Fare card. And we may need to use the PN532 card readers for the Felica system. So, different cards may have different protocol and different operation. We want to find some common operation in both systems. There's an example here. We know that both systems have an operation called read-UID. We hope to implement a complete Ruby object model to handle both systems, like the following code here. We hope to define a unified interface, RFID reader, to handle both PN532 and MFRC522 for different 2 cards. We also have separate gems for MFRC522. Because there is no similar library for this card, so we implement it from scratch. For the Felica system, we adopt the gem NFC. This is the wrapper developed by Tenderlove, which is his talk and another hole. Okay, but big thanks to him. Okay, next, the concurrent model of Tamashii is multi-thread and event-based. We know that the multi-thread program is harder to debug and is more unreadable. It also consumes more resources on devices. So the early version of Tamashii is single-threaded. All operations are controlled in a single large loop. We have a very small example here. Imagine you want to play a song when your RFID reader successfully read a card. Without the event-based approach, you may have following code. We will first initialize two components. Then we will start a loop that continuously checks the RFID reader in the non-blocking manner. When it successfully reads the data, it will call the buzzer beep method to play the song. The beep method here is blocking, because it is unreasonable to play two songs simultaneously. If there is no card available, we will sleep for a while to save CPU cycles. Okay, so what is the problem here? Because this is a single thread system with synchronized method code, so it may crash the whole program when one of these hardware components stops working. For example, when the buzzer component here stops working, it may block the whole program, and the thread is hanged here. We can continue to read another card. So, because of this, the later version of Tamashii will use the multi-thread and event-based approach to resolve this issue. The component will have their own worker thread, so they will communicate with each other with events. This is the figure describing the event model I mentioned above. We will introduce an extra component called master in the middle. Then it will manage the events between the components. We will first register those components to the master, and then when the card reader reads the card, it will emit an event to the master thread. Then the master thread will bypass the event to the buzzer. The example here, we will emit an event called RFID data, and then the event will be bypassed to the master, then will be dispatched to the component. And finally, we will play the sound in the buzzer. So with this model, we can prevent the issue when the buzzer stops working. We will only have a lot of events that's queued over layer, and we can limit the size of event queue, so we can discard the overflow event without blocking the main thread and the RFID thread. This is the example code described in the previous model. We will initialize three components, including the master here, and then we will register them to the master component. The buzzer will register a handler to play three songs when it receives the RFID data event. Then, in the reader loop, the RFID reader will only emit an event called RFID data. The emit operation here is asynchronized, so the program will not be blocked when the buzzer stops working. Although rewriting in this event-based manner needs more lines of code, however, it provides better stability and extensibility. We will have another example to showing the extensibility of this model. For instance, if we want to show extra messaging on the LCD display, only thing we need to do is to write another handle like this, display on RFID data, then print the payload. This is what we need. And there is no notification needed on the RFID reader program. In addition to prevent a program crash from single computer failure, another reason to use the multi-thread model is to restart the component individually. Sometimes the internal data structure may crash for one component. The most effective way to clean is to clean all the data and restart the worker driver. So with this multi-thread design, starting a component is very easy and almost no interfere with other components. Only thing we need to do is to call the cleanup handler, and restart a worker thread. Now, in the last part of the client side, I would like to talk about the networking model. To cooperate with previous event-based model, we will use an asynchronous connection model here. In this model, the request and response are no longer paired. That is, server can discard the request from the client, and there may no response to the client. Meanwhile, the server can push data to client without any request from the client. Under such a synchronized condition, client do not know when to receive the data. So the client will not wait on the request when you want to send the data to the server. Instead, the client will create a request object. We will call it future-based request, and it will have corresponding callbacks on it. For example, we want to read the data from user. We will create a request with type RFID data, and the card number is payload. We will also provide a callback here, a Ruby block, when the response is back to the client. It will play one song when the request authentication is true, or play 3 songs when the result is false. When the request is created, it will put the request into a Ruby object called request pool, and the Tamashii worker will send the request to the server, and you will receive the response from server and call the callback with the payload from server. For example, here the hash with auth is true, and you will play one song in the browser. Again, our request object is mainly based on the future object, so we call it a future-based request. Future object is from the gem concurrent Ruby. Every request here is a future. The future is an object that it can connect with a callback and some parameter. When it is fulfilled, one of the callback will be called in the future object. In our model, when the request is received from the server, we will call the callback in the request object. In the example above, there is also another component called the request pool. Request pool will send the request to the server, and you will receive corresponding response from server and mark the request as fulfilled. In addition, the request can also be timed out. When the request does not receive its response in some time limit, it can invalidate itself and remove it from the pool. Then we will inform the client that this request is expired. Okay. Because the client only creates a request and place it into the pool, so we need another worker thread that do the actual networking task. The worker thread will pick the request from the pool and send it to the server. It also receives the response from server and dispatch them to corresponding requests if it exists. In addition, if there is any server commands, for example reboot or play song, the worker will emit events based on that server command. The WebSocket protocol we will rely on the gem WebSocket driver, and the low-level networking I/O handling is built on the gem new I/O for Ruby. Both these two gems are famous gems that's already used by Rails. Here is the client architecture overview. The Tamashii client is built on many powerful gems, and I will have a big stem to them. Here are some important gems that we built with Tamashii client. Okay. Now in the last part, I will talk about the server detail. In next section, I will focus on following 3 aspects. The first, we manage our website client with Redis. With this, we can exchange messages between client and server. The next is Rails hook. One purpose of Tamashii is to make it easier to integrate with Rails. So the Rails hook acts like the Rails middleware. It can monitor the traffic from client and forward it to your Rails application. Then you can process the data with Rails logic. For example, you can store the data into the database or include background jobs. Last, we will talk about the model wrapper. Like a device wrapper at the client side, the model wrapper will wrap the details of Tamashii device into a model-like object. So the web developer don't need to know the tedious protocol behind the Tamashii machines. We will take a look at the WebSocket server first. A major part of our server is actually inspired by the action cable. It's the WebSocket server in the Rails. I will not talk too much about the WebSocket implementation here because you can find many articles about the action cable implementation on the internet. We extend it and make it more suitable for managed devices. We also use the Redis as the storage. Because many modern web servers, such as Passenger and Puma, support multi-thread and multi-process. To share data between different processes, we need the help from Redis. Redis has the publish and subscription feature. It allows us to run a callback when someone has sent message to Redis. For example, we have 3 clients here. Client 1 and client 2 will subscribe to the Redis channel with callback. After that, the client 3 will publish a message hello to the Redis, and Redis will inform 2 clients, client 1 and client 2, and call the callback. The next is the Tamashii Rails hook. The Tamashii Rails hook allows you to receive the traffic from the client devices. After mounting the Tamashii at the config route.rb and put some initializer script under the config initializers, you can use the Tamashii just like the Rails controller. The traffic data from the client devices will be passed to the controller that defined under the app Tamashii directory. Inside the Tamashii controller, you can do everything available in a Rails environment, such as access the database or include some background jobs. You can also send a message back to the devices. We will talk about this later. We will first look at the example code for using Rails hook. You can also find this code on our Tamashii website. The packet data will passed by the parameter of this method. We will first extract the data from this packet. Then, we will build the response packet here. In this example, we only play the one sound for the card with ID 1234. We will pack this response into JSON format, and then we will serialize this data, and finally we will send the data to the devices. Now let's talk about the model wrapping. The model wrapping at the server side is similar to the device wrapping at the client side. The developer don't need to know the detailed protocol between the server and client. Sending a command to a device simply call the method. The example here is to find a device with serial number 1234, and after that you can call the method back with parameter 3 to make it play 3 songs. In addition to the regular commands, Tamashii also provides some special callback. We can run custom callback when the devices are connected on finish authentication or close a connection. This is similar to the before save callback in the active record. Again, our work is based on many excellent gems. This figure will show some important gems that Tamashii service depends on. The convention is based on new I/O for Ruby and concurrent Ruby WebSocket driver, and we use the rack-based server, so we need rack. And the storage use Redis, so we need to start a Redis server on the server side and use the gem Redis here. Okay, in conclusion, we briefly go through some important ideas in the Tamashii, and we show some project that's based on it. We focus on providing an easy way to manage the device in Ruby and easily integrate to a Rails application. Tamashii is still under development. These features mentioned above are mainly finished, but we need more time to refactor and optimize it. Besides, the Tamashii currently only supports a very small subset of the devices on Raspberry Pi, so we hope to support more devices in the future. Here is the device list what we already support in our Tamashii system. There are 4 categories: browsers and RFID reader, LCD displays, and keyboards. Keyboards are not the usual keyboard used in your personal computer. This is for embedded system. It has 16 keys and you can touch on it. The Tamashii is an open source project, so there are many. We have some repository about the Tamashii, including the WebSocket framework, the server side, and the client side. We also have the agent. Agent gem is the client module on Raspberry Pi. We also have the manager. Manager is the server module that based on Rake. You can mount you can add the Tamashii manager into your gem file. Then you can embed the Tamashii manager into the Rails application. And we also have a repository for tracking system. This is based on the above Tamashii system. You can find more information in our website, https://tamashii.io. Okay, this ends my talk about Tamashii. Thank you for your listening.
Hello. Thank you very much for your cool talk. That was really nice. I have a couple questions, and well, the first one is recently we hear a lot about the lack of security in IoT devices, and I was wondering how your server and clients authenticate to each other.
Sorry, so you say server and client and
How do they authenticate to each other? Is there a risk that like a rogue server comes in and just talks to my devices?
Currently we only implement a synchronized token. It's like the pre-share key in the server-side and client-side configuration. So they will agree on the same password, and we will allow the authenticated devices to connect to our server, and will block other connections.
Okay. Okay, thanks.
Okay, thank you.
Second question, and last one. How does the server side know what kind of methods are implemented on each devices? I saw that you wrote like device.find.deep on the server side. How does the server know what methods are available?
Yeah, it's because we want to implement a unified interface. So we will use the intersection set of those devices. For example, if one operation is not available on another device, we will not expose the operation to the server, or we will have some option that this is an optional operation, may not be supported by some devices.
Okay, thank you.
Thank you.
Thank you for your talk. Do you have plans to support CJK characters such as kanji and katakana in I2C?
Is that hardware devices? Okay. The LCD display we used on this module only can display ASCII text, because the other character, for example, Japanese or Chinese word, is much more expensive to buy a device like this.
Thank you.
If you try to display Japanese words on it, you will display some random text on it. Very weird.
I think very difficult in my level.
Yeah.
Thank you for talking. And I'm quite interested about your open source object, and I want to know what other device want to support in the future. For example, the AD or the DC, and because I have seen the README in the GitHub. You have support for the I2C and SPI and UIST. So I think you can support for many devices.
Yeah.
If we have the project.
Yeah, but it need many works because there are a lot of devices around the world, so it may be a hard work to do so.
So
what I said that because we support the SPI, UART, and I2C interface, but there is a lot of devices, so they have different protocol. So we cannot support many of them currently. We need help from everyone to contribute to the drivers.
So you mean now you support the device you support is the typical device for the different project. Is it right?
I don't understand your question.
Oh, it's okay. I can understand.
it's time to finish this session. So if you have a question, please ask him after this session. Thank you so much.